Far out in the solar system, a world exists with rivers and lakes that are not made of water. This is Titan, Saturn's largest moon, shrouded in a perpetual orange haze. Its seas are frigid liquid methane, flowing under a dense nitrogen sky. And in those alien waters, scientists believe a form of life unlike any on Earth could be waiting. By the end of this journey, you will understand the compelling case for these methane-based organisms and how we might soon discover them. We will explore the strange chemistry that hints at their existence and the upcoming mission that could prove it. What does it mean for life to thrive in a place where water is solid rock and the air is a poisonous soup? The answer could redefine our place in the cosmos. What would it mean to find we are not alone in our own solar system? Titan is a world of profound contradictions. It is the second largest moon in our solar system, even bigger than the planet Mercury, yet it feels nothing like our own rocky companion. Its surface is hidden beneath a dense, perpetual orange haze, an atmosphere so thick that the pressure at ground level is about 50% greater than the air pressure we feel on Earth. This shroud is mostly nitrogen, just like our own sky, but that is where the similarities abruptly end. The temperature here is a constant, crushing -179 degrees Celsius. At that unimaginable cold, water is frozen solid into a substance harder than granite, and the chemistry of life as we know it grinds to a halt. But Titan has its own recipe for a world. Instead of a water cycle, Titan operates on a methane cycle. Here, methane plays the role that water does on Earth. It evaporates from vast, dark lakes, forming thick, smoggy clouds in the nitrogen sky. These clouds then release a slow, drizzling rain of liquid methane and ethane, another simple hydrocarbon. This rain carves river channels and canyons into the icy bedrock, feeds sprawling deltas, and fills immense seas that sprawl across the polar regions. The Cassini spacecraft, which orbited Saturn for 13 years, used radar to peer through the haze and map these features, revealing a landscape eerily reminiscent of home. We saw coastlines, islands, and even evidence of waves. The Huygens probe, which Cassini carried, gave us our only ground-level view. Its descent images showed a pale, pebble-strewn plain cut by dark drainage channels, a snapshot of a truly alien yet strangely familiar geology. This is not a dead, static world. It is a dynamic, active planet in miniature with its own alien weather, its own alien rivers, and its own alien seas. And in that profound strangeness lies the first clue to a monumental possibility. These alien seas have names. In the perpetual twilight of Titan's North Pole, vast, dark expanses sprawl across the landscape, the largest of which is called Kraken. It is a sea in every sense of the word, estimated to be larger than Earth's own Caspian Sea. Just to its west lies Ligeia Mare, another immense body that appears almost perfectly smooth and dark in radar images, like a pane of obsidian glass set into the icy crust. These are not water, they are cold, slow-moving soups of liquid hydrocarbons, primarily methane and ethane, with a significant amount of nitrogen dissolved within them, much like carbon dioxide is dissolved in a soda. This nitrogen can fizz out suddenly if conditions change, a phenomenon we have no direct parallel for on Earth. The depth of these lakes was a mystery until scientists used Cassini's radar in a clever way. By measuring the time it took for the radar signal to bounce off the liquid surface and then off the seafloor, they estimated Ligeia Mare to be up to 160 meters deep in places, deep enough to submerge the Washington Monument. Their shorelines are complex with bays, inlets, and islands, shaped by that same slow methane rainfall and geological forces. But the experience of standing on one of these shores would be utterly unlike standing by an earthly ocean. The atmosphere is so thick and the gravity so low, only about 14% of Earth's, that it severely dampens any wind-driven waves. The waves on Kraken-Mare are calculated to be mere centimeters high. The surface of these hydrocarbon seas would be predominantly calm, creating vast mirror-like surfaces that perfectly reflect the hazy orange sky above. It is a landscape of profound and eerie stillness, a world where the very concept of a wave is reduced to the faintest of ripples. And in that profound stillness, in those deep, dark, and chemically rich pools, the stage is set for a revolution in biology. But what exactly are we looking for when we search for life in such a place? The question is more profound than it seems. For centuries, our definition of life was based on a single example, the one thriving all around us on Earth. To move beyond that bias, scientists have worked to craft a more universal definition. One widely used framework comes from the National Aeronautics and Space Administration, which describes life as a self-sustaining chemical system capable of Darwinian evolution. Let us break that down into simpler terms. First, a self-sustaining chemical system. This means an entity that takes in raw materials and energy from its environment and uses them to build, repair, and maintain itself. Think of a plant using sunlight, carbon dioxide, and water to grow. Second, and crucially, it must be capable of Darwinian evolution. Over generations, through random changes and natural selection, the system can adapt to its environment. It is not static, it changes and diversifies over time. This definition is powerful because it focuses on processes, not on specific ingredients like water or oxygen. And that is the key to unlocking Titan. On our planet, water is the universal solvent, the liquid medium where the chemistry of life happens. Our cells are mostly water. Our metabolic reactions occur in water. Oxygen is the powerful electron acceptor that many organisms, including us, use to burn fuel for energy in a process called respiration. But these are just Earth solutions. They are not universal laws. For a hypothetical organism on Titan, water is not a solvent, it is bedrock. The liquid medium is the methane and ethane of the lakes and rivers. And oxygen is virtually non-existent in that environment. So what would take its place? The energy might come not from sunlight, which is incredibly faint on that distant moon, but from chemical sources within Titan itself. The building blocks might not be the complex carbon chains we know, but perhaps simpler, more stable structures that can form in the deep cold. This means Titanian life, if it exists, would be built from a completely different chemical toolkit, operating under rules we are only beginning to imagine. It would be a shadow biosphere, a parallel experiment in existence running alongside our own, separated by 1 billion miles of space and a fundamental divergence in chemistry. The search for life on Titan begins with a strange and ancient form of life right here on Earth. Deep within oxygen-starved swamps, buried in the mud at the bottom of lakes, and thriving in the extreme pressures around deep-sea hydrothermal vents, there exist microbes that breathe a world we would find poisonous. These are the Methanogens, a group of single-celled organisms belonging to an ancient domain of life called archaea. They are not bacteria, though they are just as small. They represent one of the oldest lineages on our planet, a living window into a time before oxygen filled our atmosphere. Their existence is a masterclass in biochemical flexibility, and their signature is the gas they release as a waste product, methane. You know the bubbles that rise from a stagnant pond or a marsh. That is often the work of methanogens. They live in the digestive tracts of cows and termites, responsible for a significant portion of Earth's natural methane emissions. Their survival strategy is beautifully simple, yet it powers a complete living system. In the absence of oxygen, they consume basic, abundant ingredients, carbon dioxide and hydrogen gas. They use these simple molecules in a chemical reaction that provides them with the energy to grow and replicate. The exhaust from this process, their metabolic waste, is methane. This is not a side effect, it is the core of their biology, the chemical trick that defines them. They are living proof that a complex organism can be built on a foundation of very simple chemistry without any need for sunlight or oxygen. This makes them the single most compelling template, the closest analog we have for what life might look like on a world like Titan. If our planet can host life that thrives on carbon dioxide and hydrogen to make methane, then why could Titan not host life that thrives in liquid methane, using other available chemicals to power itself? The Methanogens show us the blueprint is possible. They are a demonstration that the fundamental processes of life, energy capture and replication, are not bound to our particular set of ingredients. They can be built from a different menu using recipes written in a different chemical language. This chemical blueprint from Earth's ancient past gives us a direct line to the lakes of Titan. If life exists there, it would not be a carbon copy of our Methanogens, but it might follow a similar, brilliantly simple chemical logic. This is the core of the Titanian Methanogen hypothesis, a compelling idea championed by astrobiologists like Chris McKay and Heather Smith. They propose a possible metabolism, a way for a microbe to make a living using the most abundant resources on that frozen moon. The equation is strikingly elegant. Hydrogen gas plus acetylene yields methane. In plain terms, a hypothetical organism could breathe in hydrogen from the thick atmosphere and consume acetylene, a compound that likely rains down onto Titan's surface and accumulates in its lakes. By combining these two ingredients in a controlled chemical reaction inside its cell, it would release energy to sustain itself, and it would exhale methane as its waste product. Think of it as the Titanian version of how we breathe in oxygen and exhale carbon dioxide after burning our food. This single, simple reaction solves multiple problems at once. It provides a steady source of biological energy in a world where sunlight is a faint, distant glimmer and geothermal heat is uncertain. It uses compounds that are demonstrably present and abundant. And it explains a persistent mystery about Titan's atmosphere. Observations from the Cassini spacecraft showed that hydrogen gas, which should be mixing down from the upper atmosphere to the surface, is disappearing at ground level. Acetylene, which scientists expected to coat the moon's surface, also seems to be in unexpectedly short supply. It is as if something at the surface is consistently consuming both of these chemicals. The methane waste from this theoretical life would then bubble back into the lakes and atmosphere, completing a cycle. For such an organism, the frigid liquid methane of Krakenmeer would not be a deadly poison. It would be the essential medium of life, its internal solvent, the way water is for every cell in our bodies. It would be the fluid that carries nutrients, flushes out waste, and allows its internal chemistry to function. This hypothesis transforms Titan from a merely fascinating geological world into a potential biochemical one, a place where the very gaps in our chemical models point toward a breathtaking possibility. This missing hydrogen is one of the most intriguing puzzles Cassini left behind. The spacecraft's instruments painted a detailed picture of Titan's complex atmospheric chemistry. High above the surface, in the upper reaches of the orange haze, ultraviolet light from the distant sun constantly breaks apart methane and other molecules. This process, called photochemistry, acts like a giant, slow-moving factory, producing a shower of more complex organic compounds that drift down to the surface. One of the simplest and most abundant products of this process is hydrogen gas. Think of it as the lightest possible building block, a molecule that wants to float. In a world without life, this hydrogen should behave in a predictable way. It drifts down through the thick atmosphere, mixes near the ground, and because it is so light, much of it should eventually escape back into space. But the balance should be measurable. Cassini's data revealed something startling. The hydrogen produced up high was flowing down to the surface as expected, but then it simply vanished. It was not accumulating in the lower atmosphere, and the rate at which it was disappearing was faster than any known non-biological process could easily explain. It was as if the surface of Titan was acting like a sponge, soaking up this fundamental gas. In the sterile language of a scientific paper, this is called an anomalous depletion. But in the language of exploration, it sounds like a clue. On Earth, a sudden, unexplained depletion of a gas in a specific environment can sometimes signal biological activity. We see it in closed ecosystems, in soil samples, in the depths of the ocean. Something is consuming the resource, so the question becomes what on Titan's surface could be eating hydrogen. The most exciting possibility is that hypothetical methanogens are using it as their food source, combining it with acetylene to extract energy and survive. This would neatly explain the missing hydrogen and the missing acetylene in one elegant biological package. Yet scientists are rightfully cautious. A clue is not a conviction. There could be non-biological explanations, a strange, unknown chemical reaction occurring on the icy bedrock or within the lake sediments that scrubs hydrogen from the atmosphere without any life involved. Perhaps a mineral catalyst we have not yet considered is at work. The beauty of this mystery is that it is testable. It gives a future mission a very specific thing to hunt for, a chemical signature that could either point toward a living world or a fascinatingly complex dead one. The disappearance is a silent question mark written in the atmosphere of a distant moon. That missing hydrogen is only half of the chemical mystery. The other piece involves a compound called acetylene. On Earth, acetylene is best known as the gas used in welding torches, a highly flammable fuel. On Titan, it is a natural and expected product of that same atmospheric photochemistry. Sunlight constantly breaks apart methane molecules in the upper haze, and the fragments recombine into more complex organic compounds. Computer models of this process have long predicted that one of the most abundant products raining down on Titan should be acetylene. Over billions of years, this steady drizzle should have coated the moon's surface in a thick layer of acetylene snow or sludge, perhaps several meters deep. It should be everywhere, yet when the Cassini spacecraft analyzed the surface composition, it found something startling. The expected blanket of acetylene was not there. The surface seemed to have far less acetylene than all the models predicted. It was another ingredient that had gone missing. So we have two vanishing acts, hydrogen gas disappearing at the ground and acetylene failing to accumulate on the surface. Independently, each gap could have a geological or chemical explanation, but together they point toward a single, elegant biological possibility. If hypothetical methanogens exist in Titan's lakes or damp sediments, they would need both a food source and an energy source. Acetylene could be the food, the carbon-rich molecule they consume. Hydrogen gas could be the energy source, the chemical spark they breathe in to metabolize that food. Their waste product would be methane, which bubbles back into the environment, completing a tidy, self-contained cycle. This pairing of clues is what transforms a curious anomaly into a compelling hypothesis. It is circumstantial evidence, not proof. No one has seen a Titanian cell. There could be an unknown mineral on the icy surface that catalyzes a reaction between hydrogen and acetylene, scrubbing both from the environment without any life involved. Perhaps the acetylene is being buried or dissolved in a way we do not yet understand. But the biological explanation has a powerful simplicity. It uses two mysteries to solve each other. Life as a process is inherently a chemical imbalance, a system that consistently consumes resources and produces waste in a way that defies sterile equilibrium. The simultaneous depletion of hydrogen and acetylene on Titan is precisely the kind of persistent chemical imbalance that, here on Earth, would make any astrobiologist's heart beat faster. It is a pattern that whispers of a hidden metabolism. Yet this elegant biological story is not the only possible explanation for the chemical gaps in Titan's atmosphere. Before we can claim a discovery that would shake our understanding of the universe, we must exhaust every non-biological possibility. Science demands that we follow the evidence, not just the hope. So what other forces could be at work, scrubbing hydrogen and acetylene from the environment without a single living cell involved? The answer may lie in the very rocks and liquids that make up this alien world. Consider the surface of Titan. It is not a blank slate. It is a complex landscape of water ice as hard as stone, mixed with other frozen organic compounds. This ice is not pure. It is likely laced with minerals and other materials that could act as catalysts. A catalyst is a substance that speeds up a chemical reaction without being consumed itself. On Earth, we use catalysts in everything from refining gasoline to the catalytic converter in your car. On Titan, certain minerals on the surface, or even particles suspended in the methane lakes, could be facilitating reactions between hydrogen and acetylene. Imagine a speck of cosmic dust or a unique crystalline structure in the ice that provides a perfect meeting place for these molecules. They collide on its surface, react to form methane and other products, and then drift away, leaving the catalyst ready to do it again billions of times over. This process would create the same chemical depletion we observe, a relentless, abiotic consumption of resources. Furthermore, the lakes themselves are not simple methane. They are complex chemical soups containing dissolved nitrogen, ethane, and a zoo of other organic molecules. Within this dark liquid, purely chemical reactions we have never witnessed could be occurring, driven by the extreme cold and pressure. There is also the lingering power of sunlight. While faint, the ultraviolet light that reaches Titan's upper atmosphere is incredibly energetic. It is possible that some secondary photochemical process, a cascade of reactions we have not yet modeled perfectly, is responsible for breaking down acetylene before it ever reaches the surface or for binding hydrogen into other, heavier molecules that we cannot easily detect. The history of planetary science is filled with moments where a strange signal was later explained by a novel geological or chemical process, not biology. It is a necessary caution. The simultaneous disappearance of hydrogen and acetylene is a tantalizing pattern, a whisper in the data, but a whisper can be an echo of many things. It could be the faint metabolic hum of a hidden biosphere, or it could be the grinding of a strange, sterile chemical machine we are only beginning to comprehend. This tension is what makes the mystery so powerful and so real. The whispers in the data lead us to a profound and beautiful question. If life is there, swimming in the dark currents of Kraken Mare, what would it actually be? While we cannot see it, the principles of chemistry and biology allow us to sketch a science-based portrait of a truly alien being. This is not fantasy, it is an exercise in following the logic of Titan's environment to its ultimate, living conclusion. Given the extreme cold and the nature of its liquid methane world, the first and most reasonable assumption is that these methanogens would be microscopic, perhaps even smaller than most bacteria on Earth. They would be single-celled, a self-contained vessel of alien biochemistry adrift in a vast, cold sea. But that vessel would need a boundary, a wall to separate its delicate internal machinery from the outside world. On Earth, every cell is wrapped in a membrane made of molecules called lipids, which have watery heads and oily tails. This structure works perfectly in water, but it would be a disaster in liquid methane. Those oily tails would dissolve instantly, like a soap bubble popping in a vacuum. So a Titan cell would need a membrane built from molecules that are stable in hydrocarbons. Scientists like chemical engineer Paulette Clancy have theorized about alternatives. One strong candidate is a membrane made from acrylonitrile, a small, nitrogen-containing molecule that has actually been detected in Titan's atmosphere. These acrylonitrile molecules could link together into tiny, hollow spheres, creating a flexible, stable container in the methane sea. Picture not a soft, fluid bag like our cells, but something more like a microscopic, resilient bubble, a natural submarine built for hydrocarbon oceans. Inside this protective shell, the real magic happens. the cell's metabolism, that hydrogen plus acetylene reaction, would need to be carefully managed. Enzymes, the protein machines that drive all biochemistry, would have to function at -179 degrees Celsius. Earth enzymes would freeze solid and shatter. Titanian enzymes would need to be built differently, perhaps with more rigid, compact structures or using alternative chemical groups that remain flexible in the deep cold. Their internal fluid, the solvent that fills the cell, would not be salt water. It would likely be a mixture of chemicals that stays liquid at these temperatures, perhaps a slurry of simple hydrocarbons and other compounds that resist freezing. This internal environment would be utterly alien, a slow-moving, viscous gel where chemical reactions proceed at a deliberate, glacial pace compared to the frantic pace of our warm, watery cells. Reproduction might be a rare and energy-intensive event, with cells dividing only after centuries of gathering enough resources. They would not be fast, bustling microbes. They would be patient, ancient things, living lives of profound slowness in an endless, dark twilight. Their entire existence would be a testament to the adaptability of the living process, proving that biology can write its instructions in more than one chemical language. The portrait of a possible cell gives us a target, but where on this vast, complex moon should we aim our search? Titan is not uniformly hospitable, even to its own hypothetical life. We must think like explorers, identifying the oases in this frozen desert where the conditions for a living chemistry are most ripe. The most obvious and compelling candidates are the very features that make Titan unique, its liquid methane lakes and seas. Within those dark, still bodies, the highest probability for life lies at a specific boundary, the sediment-water interface. Picture the muddy bottom of a lake on Earth, teeming with microbial activity. On Titan, the lakebed sediment would be a sludge of organic compounds, tholins, and water ice grains that have rained down for eons. This layer could act as a concentrated pantry, trapping and storing nutrients like acetylene. A hypothetical methanogen nestled in this sediment would have a steady supply of food from above and a stable surface to cling to, all while bathed in the liquid methane solvent it needs. The sediments might also offer protection from any harmful radiation or chemical processes at the very surface. These lake floors are the prime real estate, the most likely neighborhoods for Titan's first inhabitants. Yet the lakes themselves are not the only possibility. There is another, more hidden realm that could harbor an entirely different kind of life. Deep beneath the icy crust, scientists believe Titan may host vast subsurface oceans of liquid water, kept from freezing by the heat of radioactive decay and tidal forces from Saturn's immense gravity. This water would not be pure. It is likely a briny, ammonia-rich mixture, a potent antifreeze. In this warm, dark, watery environment, the rules change completely. Here, the familiar chemistry of Earth-like life, using water as a solvent, becomes possible again. Any organisms in this deep ocean would be cut off from the surface, deriving energy not from sunlight or atmospheric chemicals, but from hydrothermal vents on the seafloor or from chemical reactions between the water and the rocky core. This would be a biosphere completely independent of the methane lakes above, a secret ocean within an ice moon. The existence of two potential habitats, one hydrocarbon based on the surface and one water-based below, makes Titan a double mystery. It is conceivable, though wildly speculative, that both could exist, two separate genesis events on a single world. Beyond these two extremes, there are fringe habitats. The damp, porous, icy crust between major lakes could act like a cold, hydrocarbon-soaked sponge, hosting microbes in tiny pore spaces. The shorelines, where liquid methane slowly seeps into the ground, could create a nutrient-rich gradient, a kind of tidal zone for alien biology. Each location presents a different set of challenges and energy sources, painting Titan not as a single world, but as a collection of potential biomass. Our search must be strategic, prioritizing the places where the whispers in the data are loudest, where the chemical imbalances are most pronounced and where a fragile spark of metabolism would have the best chance to catch and hold. The chemistry of life on Titan would unfold in a world of profound stillness, not just of landscape but of time itself. At -179 degrees Celsius, the frantic dance of molecules that powers every cell on Earth slows to a glacial crawl. Chemical reactions that happen in milliseconds in our warm bodies could take days, years, or even centuries in the cold hydrocarbon seas. For a hypothetical organism, this is the ultimate constraint, the defining challenge of its entire existence. How do you build a living, evolving system when the very particles you are made of move with such reluctant slowness? The answer forces us to rethink the most basic rhythms of biology. First, consider the engines of life, enzymes. On Earth, these are complex protein machines that speed up vital reactions by millions of times. But at Titanian temperatures, most Earth-like proteins would lock into rigid, useless shapes. Any enzymes used by Titanian life would need to be masterpieces of molecular architecture, built from different amino acids or structures that remain uniquely flexible in the deep cold. They would need to be exquisitely efficient, perhaps acting as templates that hold reactant molecules in perfect alignment for far longer, coaxing them to react despite the energy-sapping cold. Even with such perfect machinery, metabolism would be an achingly slow process. An organism might need to gather hydrogen and acetylene for years just to fuel a single act of cellular repair or growth. This leads to an inescapable conclusion. The pace of life on Titan would be unrecognizable to us. Its biology might operate on a timescale of geological epochs, not human generations. A single cell division, the act of reproduction, could be an event that occurs once every century or once every millennium. An individual microbe could be thousands of years old, a patient collector of scarce chemical energy in the eternal dark. And what of the cell's interior, that protected pocket of alien biochemistry? It cannot freeze, just as life on Earth uses special antifreeze proteins to prevent ice crystals from forming and shredding cell membranes. Titanian life would need its own version of cryoprotection. But its enemy would not be ice crystals of water. In a methane solvent, the danger might be the crystallization of other compounds within its cellular fluid, or the sudden formation of solid ethane or other hydrocarbons that could rupture its delicate acrylonitrile membrane. It would need to produce internal molecules that act as antifreeze for a methane-based system, compounds that lower the freezing point of its internal slurry and keep it in a stable, liquid state. This is a biology of extreme patience and profound stability, a whisper of metabolism sustained across eons. Contemplating it shifts our perspective. We often search for life that operates on our schedule, in our temperatures, but the universe may be filled with life that is in no hurry at all, living out epic, slow-motion sagas in the frozen dark, where 1,000 years passes in the blink of a cosmic eye. Such profound slowness demands an equally reliable source of fuel. In the eternal twilight of Titan's lakes, energy is the ultimate currency, and life would need a steady way to earn it. The hydrogen plus acetylene reaction is the most elegant and talked about menu, but it is far from the only item on the potential buffet. To survive and perhaps even diversify, organisms would need to exploit every possible chemical opportunity. This brings us to a fundamental concept in all of biochemistry, redox chemistry. The term sounds technical, but the idea is beautifully simple. It is the trading of electrons. Think of it as a universal barter system for energy. One molecule donates electrons, it gets oxidized, while another molecule accepts those electrons, it gets reduced. This electron flow is what powers everything from a roaring fire to the quiet hum of a cell in your body. On Earth, we are familiar with oxygen as the ultimate electron acceptor, the hungry molecule that takes electrons from our food. On Titan, oxygen is absent, so life would need to find other electron acceptors. the entire environment becomes a different kind of trading floor with a unique set of commodities. The liquid methane and ethane themselves are not food, they are the inert background solvent. The real nutrients are the other compounds dissolved or floating within them. So what else is on the menu? Ethane is abundant in the seas, but it is a very stable molecule like a finished product. Using it for energy would be difficult, like trying to burn ash. A more promising possibility involves other, more reactive organic molecules that constantly rain down from the orange haze above. This complex tarry substance is called tholin, a word derived from the Greek for muddy. Tholins are not a single compound, but a vast mixture of different hydrocarbons and nitrogen-bearing molecules, the result of sunlight breaking apart methane and nitrogen and gluing the pieces back together in random, complex ways. They are thought to give Titan its reddish-brown color and coat its surface in a sticky, organic sludge. For a microbe, this could be a treasure trove. Certain components of tholin might be rich in chemical bonds that can be broken to release energy. An organism could learn to crack open these complex polymers, harvesting electrons in the process. Another potential reaction could involve hydrogen and more complex molecules than acetylene. Or perhaps life could use the dissolved nitrogen in the lakes, finding a way to incorporate it into reactions that release energy, a process called nitrogen reduction. The key insight is that while energy is profoundly scarce compared to a sun-drenched Earth, Titan's environment is not chemically barren. It is a slow, steady drip feed of organic building blocks. Different microbes, if they exist, might specialize in different reactions. Just as on Earth we have bacteria that breathe oxygen, others that breathe sulfate, and still others that breathe iron. This opens the door to a breathtaking possibility: ecological diversity. In the dark, cold depths of Kraken Mare, there could be multiple species, each with its own metabolic niche, forming a simple but real food web based entirely on chemical trading. One type might consume hydrogen and acetylene, excreting methane. Another might feed on the waste products of the first, or on a specific component of the tholin rain. They would not hunt or graze, they would catalyze and consume, living out eons-long lives as chemical artisans in a frozen sea. The very scarcity of energy could force life into a variety of specialized forms, each perfectly adapted to exploit a tiny, specific corner of Titan's vast hydrocarbon kitchen. This profound difference in chemistry forces us to confront the ultimate question of building life itself. Water is not just a passive backdrop for biology on Earth, it is an active, indispensable architect. Its unique properties, which we take for granted, are what make our kind of life possible. Water is what chemists call a polar solvent. This means its molecules have a slight electrical charge with a positive end and a negative end. This polarity allows water to dissolve a vast array of substances, particularly salts and other charged molecules, pulling them apart and keeping them in solution where they can interact. More importantly, this polarity is crucial for forming the very structures of life. Our DNA, our proteins, our cellular membranes all rely on water's polar nature to fold into their precise functional shapes. The way a protein twists into a complex three-dimensional machine, or the way the two strands of DNA zipper together, is governed by how their charged parts are attracted to or repelled by water molecules. Water is the director of the molecular dance. Liquid methane, by stark contrast, is a non-polar solvent. Its molecules have no such charge separation. They are electrically neutral, like tiny droplets of oil. This fundamental difference changes everything about what can exist and interact within it. A substance like table salt, which dissolves instantly in water, would be utterly insoluble in liquid methane. It would simply sit at the bottom of Kraken Mare like a pile of inert sand. The complex, charged biomolecules that form the basis of Earth life would not form, or would immediately clump together uselessly in such an environment. This is the solvent problem, the single greatest chemical hurdle for life on Titan. If the liquid medium cannot support the chemistry of familiar biopolymers, then life must find an entirely different set of building blocks, a different architectural language altogether. The challenge is not just finding an energy source, but constructing the intricate, information-rich structures that can store genetic blueprints and perform the work of a cell from materials that are stable and functional in a sea of hydrocarbons. It means reinventing the wheel of biology from the molecular ground up. So what molecules could possibly play the role of DNA or proteins in a methane sea? They would need to be stable in the cold, soluble in non-polar methane, and capable of forming long, complex chains that can carry information or perform tasks. Scientists looking at this puzzle have turned to some surprising candidates from our own world. Certain plastics, for instance. On Earth, we think of plastics as synthetic, inert materials. But chemically, they are polymers, long chains of repeating units, not so different in basic structure from the proteins in your body. Some of these polymers, like polyethylene or polypropylene, are inherently non-polar and are actually quite stable in hydrocarbon solvents. In the cold, slow chemistry of Titan, similar chains could potentially form naturally through geological or photochemical processes. Imagine a biological system that uses a plastic-like polymer as its genetic material, a chain where the sequence of different hydrocarbon groups encodes information, much like the sequence of bases in our DNA. Instead of a double helix floating in water, you might have a single, sturdy strand suspended in methane, its information protected by its very simplicity and chemical stability. Another, more exotic possibility involves silicon. On Earth, carbon is the backbone of life because it can form 4 strong bonds, creating an endless variety of complex, stable molecules. Silicon, which sits directly below carbon on the periodic table, can also form 4 bonds. While silicon-based life is a staple of science fiction, most chemists dismiss it for Earth-like conditions because silicon's bonds with oxygen form very stable, inert rocks like sand, locking the silicon away. But on Titan, in a water-free, oxygen-poor environment bathed in hydrocarbons, the rules are different. Silicon might bond with carbon or hydrogen to form chains called silanes. These silane molecules could, in theory, serve as an alternative biochemical backbone. They would be fragile in our world, but in Titan's cold, protected from water and oxygen, they might have the stability needed to form the basis of a living system. These are not predictions, but thought experiments that highlight the sheer scale of the puzzle. The solvent problem forces us to expand our imagination beyond the carbon and water template. It suggests that if biogenesis occurred on Titan, it did so by discovering a parallel path, using a chemistry that to us seems inert or industrial to craft something alive. The lakes may not hum with the familiar chemistry of cells, but with the patient, silent assembly of structures we have only begun to conceive. The silent assembly of potential life demands a witness, and we are sending one. After decades of telescopes, probes, and tantalizing data, humanity is preparing for its most intimate encounter with Titan yet. A mission that will not just fly by, but land, explore, and taste the very sands of this alien world. Its name is Dragonfly, and it represents a leap in planetary exploration so bold it sounds like science fiction. Dragonfly is not a rover with wheels, but a robotic rotorcraft, a dual quadcopter drone about the size of a small car. It is designed to be an aerial explorer in Titan's thick atmosphere and low gravity, which make flying far more efficient than on Earth. Think of it not as a slow, rolling laboratory, but as a capable, intelligent dragonfly that can hop across the landscape, traveling tens of kilometers with each flight to survey entirely new environments. This mobility is key because Titan's terrain is complex, a patchwork of dunes, lakes, and impact craters that a rover could never fully traverse. Dragonfly's current schedule has it launching in 2028, beginning a long cruise through the solar system before its dramatic arrival at Titan in the mid-2030s. Its journey will end with a heart-stopping descent through the orange haze, culminating in a powered landing that will bring our senses to the surface of this mysterious moon for the first time since the Huygens probe touched down briefly nearly 3 decades prior. But where will it land? The chosen site is a region of profound scientific promise near the Selk impact crater. This area is a geological treasure trove. It features vast expanses of linear dunes, not made of sand as we know it, but of dark, organic hydrocarbon particles that have snowed from the sky for eons. More importantly, the Selk crater itself was created by an impact that blasted through Titan's surface, excavating and exposing ancient water ice from the crust below. This is crucial because where water ice and complex organic molecules meet in the presence of liquid methane is precisely the kind of laboratory where the chemistry of life could have been tested. Dragonfly will land amidst these organic dunes with the water ice rim of Selk crater within easy flying distance, giving it access to 2 fundamentally different and revealing environments. But a vehicle is only as good as its tools. Dragonfly will carry a sophisticated suite of instruments designed to answer our most pressing questions. It will have a drill to collect samples of the icy sand and a mass spectrometer to vaporize those samples and identify every molecule within them, atom by atom. It will carry sensors to monitor the weather and geology, and most importantly, it will have instruments specifically designed to study probiotic chemistry and search for biosignatures. This means Dragonfly will not just catalog what is there, it will look for the patterns that distinguish a sterile chemical process from a biological one. It will measure the ratios of carbon isotopes in organic molecules because life often prefers lighter isotopes, leaving a subtle fingerprint. It will analyze the complexity and chirality or handedness of molecules, as biology often produces molecules with a specific twist, unlike random chemistry. In essence, Dragonfly will be a detective on an alien world, sifting through the chemical evidence to determine if the whispers in Cassini's data were just the wind of strange geology or the faint, persistent hum of a living world. This is no longer a theoretical exercise. The mission is being built, the launch date is on the calendar. In just a few years, a nuclear-powered robotic Dragonfly will begin its voyage to a world of methane lakes and organic dunes, carrying with it our deepest question. Are we alone? Soon, we may finally have an answer whispered back from the shores of an alien sea. Dragonfly's toolkit transforms it from a passive observer into an active chemical detective. Its core mission is to search for biosignatures, not fossils or footprints, but the subtle molecular fingerprints left behind by living processes. One of the most powerful tools in its arsenal is the ability to measure isotopic ratios. To understand this, think of carbon atoms. Most carbon atoms have 6 protons and 6 neutrons, making carbon-12. But a small fraction have an extra neutron, making them the heavier carbon-13. They are chemically identical, but life, in its metabolic processes, often finds it slightly easier to use and incorporate the lighter carbon-12. Over time, this preference can skew the ratio of light to heavy carbon in biological materials compared to non-biological surroundings. It is a tiny signature, a 1 part in 1,000 difference, but it is a telltale clue. If Dragonfly drills into the organic dunes around Selk crater and finds that the complex molecules there are enriched in light carbon, it would be a strong indicator that biological activity shaped them. It would suggest something was selectively eating and excreting, favoring one atom over its heavier twin. Beyond isotopes, Dragonfly will dissect the very complexity of Titan's organic haze. The tholin sludge coating the surface is a chaotic mixture, a product of random ultraviolet chemistry in the upper atmosphere, but biology is not random. It builds with purpose. Life takes the chaotic buffet of available chemicals and selects specific compounds, assembles them into structured, repeating patterns, or produces molecules with a specific handedness known as chirality. On Earth, the amino acids in our proteins are almost exclusively left-handed, a signature of biological selection. If Dragonfly's mass spectrometer finds that Titan's surface organics are not a random tar, but instead show surprising selectivity, an abundance of specific, useful molecules like acrylonitrile, or a dominance of one chiral form over another, it would be evidence that a process beyond sterile chemistry is at work. It would mean the environment is not just making molecules but curating them. Most critically, Dragonfly will perform the ultimate ground truth experiment for the Methanogen hypothesis. Cassini's data from orbit gave us the puzzling disappearance of hydrogen and acetylene. Dragonfly will be standing right where that disappearance is happening. It will directly sample the atmosphere at the surface, measuring the precise concentrations of hydrogen gas. It will drill into the damp sediments and lakebed analogs, measuring exactly how much acetylene is present and in what form. By building a detailed, local model of these chemical cycles with unprecedented precision, it can determine if the consumption is uniform or patchy, if it correlates with specific materials, and if the methane produced matches what a biological metabolism would predict. It can search for other potential metabolic waste products we have not even thought to look for. This is the difference between seeing a shadow from a great distance and walking over to inspect the object casting it. Dragonfly gets to walk over. This mission represents our species' most deliberate and sophisticated attempt to answer an ancient question on another world. While rovers on Mars search for signs of past life in dried-up riverbeds, Dragonfly is hunting for the chemistry of present life in active alien wetlands. Its nuclear battery will power its flights and instruments for years, allowing it to explore multiple sites, from the organic dunes to the water ice walls of Selk Crater, building a comprehensive picture of Titan's habitability. No single measurement will provide a definitive answer. Science rarely works that way, but a convergence of evidence, anomalous isotopic ratios, patterned organic molecules, and a localized, explainable depletion of key chemicals could build a case that changes everything. The coming decades will see this robotic emissary slowly, methodically, piecing together the chemical narrative of Titan. With each gentle landing on its icy surface, we are not just collecting data. We are listening for a heartbeat in the dark. That search for a heartbeat carries with it a profound responsibility, one that weighs heavily on every scientist and engineer involved. We must ensure that the very act of looking for life does not inadvertently destroy the evidence, or worse, become an invasion. This is the core of planetary protection, a set of ethical and scientific principles that govern our exploration of other worlds. For a place as potentially habitable as Titan, these rules are not just guidelines, they are a solemn duty. Under international treaties coordinated by the Committee on Space Research, worlds are categorized based on their potential to host life and the interest they hold for understanding chemical evolution. Titan is classified as a Category 2 body. This means it is a world of significant interest for the study of organic chemistry and probiotic processes, but the likelihood of contamination by Earth life having a detrimental effect is currently assessed as low. Low, however, does not mean zero. The classification carries a crucial mandate: we must avoid contaminating it. The goal is to preserve Titan's pristine environment for our own scientific study, to ensure any discovery we make is genuinely alien and not something we accidentally brought with us. But there is an even deeper ethical layer, the possibility, however slim, that Titan already hosts its own native life forms. In that case, our robotic emissary could become an existential threat, introducing hardy Earth microbes that might outcompete or poison a fragile, alien biosphere that has evolved in isolation for billions of years. Imagine the tragedy of discovering life on another world, only to realize we were the ones who infected it. To prevent this, the Dragonfly mission undergoes an exhaustive planetary protection protocol. Every component of the spacecraft is assembled in ultra-clean rooms, environments with filtered air and strict contamination controls. The vehicle itself will undergo rigorous sterilization procedures. While it cannot be baked in an oven like some Mars rovers, due to the sensitive nature of its instruments and composite materials, it will be meticulously cleaned with alcohol-based solvents and other techniques to reduce its microbial load to an absolute minimum. Certain parts, like the drill that will sample Titan's surface, are subject to especially stringent standards, as they are the direct interface with the alien environment. The team must document and account for every microbe, every spore that could possibly hitch a ride. This is not about achieving sterility, a complete absence of all life, which is likely impossible. It is about reducing the risk to an acceptable level, a calculated balance between exploration and preservation. This ethical framework transforms the mission from a simple act of discovery into a gesture of respect. We are not conquering Titan, we are visiting it as careful guests. We are extending a principle first articulated for wilderness areas on Earth: take only pictures, leave only footprints. In this case, we aim to leave nothing at all except the gentle impression of our lander's legs in the soft, organic sand. Every measurement taken, every sample analyzed, is done with the understanding that this world is not ours to claim but to understand. The silence we listen for in the dark must remain pure, undisturbed by our own biological noise. Our greatest responsibility may be to ensure that if we do find a whisper of life, it is a song that began on Titan and not an echo of our own. The leap from a solitary cell to a complex organism is the universe's most profound creative act. On Earth, it took billions of years of trial and error in a warm, sunlit sea. On Titan, in the deep, cold, and eternal twilight, the same evolutionary pressures would face a radically different set of rules. Yet the raw materials for complexity are undeniably present, a steady rain of organic compounds over eons. So, if simple methanogens gained a foothold in those dark lakes, could the relentless engine of natural selection eventually craft something more? It is a question of staggering timescales and alien possibilities, a thought experiment at the very edge of science. The first step toward complexity is cooperation. On Earth, single-celled organisms sometimes band together into colonies for mutual benefit, a precursor to true multicellular life. In Titan's seas, a similar story could unfold with a hydrocarbon twist. Imagine a drifting mat of cells, linked by sturdy, plastic-like filaments, sharing nutrients siphoned from the methane soup. Over millions of years, such a colony might begin to specialize. Some cells on the exterior could develop structures to better capture hydrogen from the water, becoming dedicated gills. Cells in the interior might focus on breaking down complex tholins, acting as a communal stomach. This division of labor creates a new kind of entity, a slow, drifting creature perhaps the size of a dinner plate, a living raft harvesting chemical energy as it drifts with the languid currents of Kraken Mare. Its body would not be soft and fleshy, but more like a tough, flexible mat or a porous, lattice-like structure, its form dictated by the need for maximum surface area in a nutrient-poor sea. It would grow over centuries, reproduce by fracturing, and live for millennia, a patient, placid giant in a world without predators. But the true realm of wonder might not be in the lakes at all. Titan's thick atmosphere and low gravity open a door to a possibility Earth never truly explored: aerial life. Here, the air is not thin and challenging, it is a dense, buoyant ocean. Creatures could evolve to live their entire lives aloft, never touching the ground. Picture a balloon-like organism, its body a sac filled with warm methane or hydrogen produced by its own metabolism. This internal warmth, even a few degrees above the frigid surroundings, would provide lift in the dense air. It might trail delicate tendrils to harvest tholin particles or other organic aerosols from the haze. It could have simple light sensors to orient itself in the perpetual gloom, or chemical sensors to drift toward areas rich in certain gases. These would not be flapping birds or buzzing insects, but graceful, gossamer blimps, drifting on the global wind currents in kilometer-long migrations that take years to complete. Their life cycle would be a slow ballet of birth, growth, and reproduction in the orange sky, a silent ecosystem floating high above the frozen landscape. On the surface, in the damp, organic sands of the dunes, another form of movement might emerge. With energy so scarce, active hunting is likely impossible. But a creature could farm. Imagine a slow-moving crawler, a multicellular slug-like organism with a chemically hardened underside. It moves at a pace of millimeters per year, excreting enzymes ahead of itself to dissolve and pre-digest the complex tarry tholins on the surface, then absorbing the simpler nutrients. Its journey across a dune might take 10,000 years, a literal grazer on a frozen pasture of probiotic goo. Its senses would be chemical and tactile, feeling for the richest veins of organic material. In a world without fast-paced competition, the evolutionary drive would favor extreme efficiency and durability, not speed or strength. These are, of course, speculative visions. They require that life not only began on Titan, but that it found a stable, long-term energy source robust enough to power the increased demands of a complex body and a nervous system, however simple. The profound cold and slow chemistry are immense barriers to the rapid, intricate communication that complex animal life on Earth relies on. Yet, the universe has a habit of filling viable niches. If a pathway exists, no matter how long and slow, evolution will find it. Contemplating these possibilities does more than spark imagination, it reframes our search. It reminds us that life, in its boundless creativity, might not stop at the microbial. In the dark lakes and hazy skies of a distant moon, nature may have been painting with a completely different palette for billions of years, creating forms of beauty and complexity we are only beginning to dream of. This solar system is not a single-stage competition for life, but a grand exhibition of possibilities. Titan stands apart from its famous oceanic siblings, Europa and Enceladus, not as a rival, but as a fundamentally different experiment. The contest is not about which world is more likely to host life, but about how many distinct blueprints the universe might employ. Europa, a moon of Jupiter, is a world of gleaming, cracked ice. Beneath its frozen crust, perhaps 10 to 15 kilometers thick, churns a vast global ocean of liquid saltwater, kept warm by the intense gravitational squeezing of Jupiter. This ocean is almost certainly in contact with a rocky, silicate seafloor, where hydrothermal vents could provide chemical energy and minerals, much like those on Earth's ocean floor. Enceladus, a small, brilliant moon of Saturn, confirms this model. Its south pole is scarred by giant fissures from which powerful geysers blast water vapor and ice crystals into space. Cassini flew through these plumes and tasted them, detecting not just water, but simple organic molecules, salts, and even tiny silica particles that are a telltale sign of hot water interacting with rock on the seafloor. Both Europa and Enceladus present a powerful, familiar case, a water-based habitat, the very solvent of life on Earth, hidden beneath an icy shell. Their energy likely comes from geology, from the heat and chemistry of water-rock interactions in the dark. They are proof that a sun is not strictly necessary, that life's cradle can be a warm, dark, watery womb inside a frozen world. Titan shatters this template. It has no hidden ocean of water, at least not one that is the primary habitat for surface life. Instead, it wears its liquid on the outside, in plain sight, but that liquid is methane. Its energy likely comes not from geological heat, but from atmospheric chemistry, from the sunlight-driven production of acetylene and hydrogen that rains down onto its surface. Titan's potential biosphere would be built on a foundation of hydrocarbons, not water, operating at temperatures where Earth-like biochemistry would freeze and shatter. This creates a stunning triad of possibilities within our own cosmic backyard. We could have life in the subsurface water oceans of Europa and Enceladus, following a chemical path broadly similar to our own, cut off from the surface and powered by geology. And separately, we could have life on the exposed surface and lakes of Titan, following a completely alien hydrocarbon path powered by sunlight-driven atmospheric chemistry. They represent two independent solutions to the problem of existence. The water worlds offer a hidden, potentially stable environment, but one that is incredibly difficult to access or observe directly. Titan offers an exposed, accessible laboratory, but one where the very rules of biochemistry are foreign. This is the profound shift in thinking. We are no longer searching for a single, Earth-like winner in the solar system. We are exploring a portfolio of potential biospheres. Each moon presents a different combination of solvent, energy, and chemistry. Europa and Enceladus ask, can life arise again in a warm, dark sea? Titan asks a more radical question, can life begin at all without water as its solvent? The answer to either would redefine our place in the cosmos, but the answer to both would be a revelation of unimaginable scale. It would mean our solar system is not merely hospitable to life, but is a prolific nursery capable of sparking the living process in multiple, parallel ways. The plumes of Enceladus, the cracked ice of Europa, and the dark lakes of Titan are not competitors. They are chapters in the same epic story, each written in a different chemical dialect, waiting for us to learn how to read them. The profound silence of the cosmos has haunted our imagination for generations. It is the heart of the Fermi paradox, the simple, devastating question posed by physicist Enrico Fermi. If life is common in a galaxy with hundreds of billions of stars, and if intelligent civilizations arise even occasionally, then where is everybody? The universe is ancient, giving ample time for such civilizations to spread. Yet we hear nothing, see nothing. This cosmic quiet feels like a contradiction, a puzzle wrapped in the emptiness between stars. Our search for life has often been guided by a single example, our own, limiting our vision to Earth like worlds around Sun like stars. But Titan changes the parameters of the entire equation. The potential discovery of a second, independent genesis of life on that frozen moon, a form of weird life built from methane and hydrocarbons, would not just add another data point. It would shatter our assumptions about life's requirements. It would prove that biogenesis, the spark that turns chemistry into biology, is not a freak accident unique to the warm, watery conditions of early Earth. It is a robust, creative, and perhaps even commonplace process in the universe. If life can start twice in two radically different chemical environments within our own solar system, then it can start anywhere the fundamental ingredients, a solvent, an energy source, and complex chemistry come together. Suddenly, the definition of a habitable world explodes. It is no longer just the Goldilocks zone around a star where liquid water can exist. It becomes any stable environment with a liquid medium and a source of energy, whether that liquid is water under the ice of Europa, methane on the surface of Titan, or perhaps even something stranger in the clouds of a gas giant. The number of potential cradles for life in our galaxy alone could multiply from millions to billions. This revelation makes the silence of the cosmos not less puzzling, but infinitely more profound. If life is this easy, this tenacious, this chemically inventive, then the great filter, the hypothetical barrier that prevents life from reaching intelligence and spreading, becomes an even more urgent mystery. Perhaps the filter lies not in the beginning but later. Maybe simple life is common, but the leap to multicellular complexity, or to intelligence, or to a sustainable technological civilization is the true cosmic rarity. Titan could be showing us that the universe is teeming with simple, silent biospheres, microbial mats in alien seas, drifting blimps in thick atmospheres, worlds alive but never speaking. We would no longer be listening for a conversation in an empty room, but straining to hear a single voice in a galaxy full of whispers. The discovery of life on Titan would transform the Fermi paradox from a question about intelligence into a question about solitude. Are we alone in our ability to wonder, to build, and to ask the question itself, even as we float in a sea of simpler, stranger living worlds? The profound questions raised by Titan's chemistry are not left to speculation alone. Here on Earth, in laboratories sealed against our own atmosphere, scientists are building tiny, frozen versions of that distant moon. They are pioneers in a field of extreme simulation, attempting to recreate the alien conditions of Titan to watch its chemistry unfold in real time. Researchers like planetary scientist Jonathan Lunine and chemist Martin Rom have led teams that construct special chambers, vessels where they can precisely control an environment that is, by Earth standards, utterly hostile. They pump in nitrogen and methane, mimicking Titan's thick air. They then introduce a source of energy, often a cold plasma discharge or ultraviolet light, to simulate the photochemical effects of the distant sun. And then they watch. What happens is a slow, silent miracle of synthesis. Over hours or days, a reddish-brown sludge begins to coat the cold walls of the chamber. This is laboratory-made tholin, a simulated version of the complex organic goo that paints Titan orange and rains onto its surface. Analyzing this synthetic sludge is like having a recipe book for Titan's atmosphere. It allows scientists to identify which specific molecules are forming from the simple starting ingredients, and to trace the chemical pathways that could, over eons, lead to increasingly complex probiotic compounds. These experiments have confirmed that Titan's environment is a prolific factory for organic chemistry, producing everything from simple gases like acetylene and hydrogen, cyanide, to rings of carbon and nitrogen that are the precursors to the nucleobases in our own DNA. The lab becomes a time machine, compressing millions of years of atmospheric drizzle into a few days of observation, showing us that the building blocks for life, or at least for life's chemistry, are being manufactured in abundance on that frozen world. But an even more direct test involves the potential for life itself. Some experiments have taken the next logical step, introducing Earth's hardiest extremophile microbes into chambers filled with liquid methane at Titanian temperatures. The results are stark and telling. Life as we know it, even the toughest archaea from our deepest vents or coldest deserts, cannot survive, let alone metabolize or reproduce in that hydrocarbon bath. Their water-based cellular machinery seizes up, their membranes dissolve, and the liquid methane proves to be a poison, not a solvent for their biology. This is a crucial result. It tells us that any life on Titan cannot be a transplant from Earth. It must be a native product, built from the ground up to use liquid methane as its internal medium. These simulation experiments serve a dual purpose. They map the possible chemical roads that could lead toward life, showing us the steps available on Titan's probiotic ladder. And just as importantly, they show us the dead ends, proving that our kind of life hits a wall, forcing us to widen our imagination. Every batch of synthetic tholin, every failed microbial test, brings the abstract mystery of Titan into sharp, tangible focus in a lab on Earth, guiding our search and defining what truly alien life must be. These laboratory creations point directly to the most abundant raw material on Titan itself, the enigmatic substance known as tholin. That reddish-brown haze that shrouds the moon, the sticky sludge that likely coats its dunes and shorelines, is not just atmospheric decoration. It is the closest thing Titan has to a primordial soup, a vast reservoir of probiotic chemistry. The word itself comes from the Greek for muddy, and it perfectly describes this material. Tholins are not a single compound, but a vast, complex mixture of different organic polymers. They form when simple molecules like methane and nitrogen, bathed in the faint ultraviolet light of the distant sun, are broken apart and their fragments recombine at random into larger, more complex chains. It is a slow, constant process that has been running for billions of years, raining a drizzle of organic goo onto the frozen landscape below. This material is not alive. In the cold, still environment, it is chemically inert, a tarry residue, but it is probiotic, meaning it consists of the complex organic building blocks from which life could potentially arise if given the right conditions and a spark of organization. Think of it as nature's ultimate chemistry set, a random but incredibly rich library of carbon-based molecules delivered to the surface. For any hypothetical genesis of life on Titan, this Tholen sludge is the starting pantry. The question is whether the environment can move these random polymers towards something more organized, more biologically relevant. The chemical complexity within Tholen is staggering. Laboratory simulations have shown it contains rings of carbon and nitrogen similar to the nucleobases that form the letters of our DNA. It has long chains of hydrocarbons that could serve as backbones for other structures. It contains molecules like hydrogen cyanide and acetylene, which are stepping stones to more complex amino acids. But on the cold, static surface, these ingredients are frozen in place, like letters spilled from a box that have not yet been arranged into words. For the leap from chemistry to biology to occur, something must facilitate their assembly. This is where Titan's unique environment offers possibilities. While the cold slows most reactions to a crawl, it does not stop them entirely. The liquid methane lakes and damp sediments are not just solvents, they are potential mixing bowls. Within this hydrocarbon fluid, certain components of Tholen might dissolve and become mobile, able to drift and meet other molecules. More intriguingly, the surface of Titan is not chemically blank. It is made of water ice as hard as rock, but that ice is likely laced with minerals and other materials delivered by meteorites or formed in the crust. These could act as catalysts. Imagine a tiny grain of a special mineral on the lake bed, its surface providing a perfect template. As Tholen components dissolve in the methane and drift past, they might stick to this grain in a specific orientation, held close together long enough for the extreme cold to allow a slow, deliberate bond to form. Over centuries, such a process could build up a concentration of more complex molecules, like amino acids or even the precursors to nucleotides, right there in the muck at the bottom of Kraken Mare. This is a chemistry of almost unimaginable patience. A reaction that takes seconds in a warm laboratory on Earth might require 10,000 years in the depths of a Titanian lake. But time is the one resource Titan has in nearly infinite supply. Over millions of years, even these glacial processes could accumulate a significant stockpile of probiotic material. The catalysts would not be consumed, they would simply provide a meeting place over and over again for random chemistry to become slightly less random. The presence of liquid methane is crucial here, not as a solvent for Earth-like life, but as a transport medium and a reaction environment for this alien probiotic chemistry. It allows the building blocks to move, to concentrate in certain areas like sheltered coves or deep lake sediments, and to interact with solid surfaces. This transforms Titan from a world merely coated in organic tar into a world with active, if incredibly slow, chemical laboratories operating in its dark seas. The Tholens are the feedstock, the methane is the conveyor belt, and the icy minerals are the workbenches. Whether this process has ever crossed the threshold from interesting chemistry to a living system is the ultimate mystery. But the pathway exists, the ingredients are there, mixing in the eternal twilight, following a recipe written in the laws of physics and chemistry that we are only beginning to translate. The story of Titan is a story of human vision slowly coming into focus. For centuries after its discovery by Dutch astronomer Christian Huygens in 1655, it was merely a point of light, a star-like companion to the ringed planet Saturn. Telescopes improved, revealing it as a moon, but one shrouded in mystery. Its distinctive orange hue hinted at something unusual, yet its surface remained a secret. The first true glimpse came from the twin Voyager probes in the early 1980s. As Voyager 1 sped past, its cameras captured Titan as a fuzzy, featureless apricot, a world completely veiled by its own thick, smoggy atmosphere. The data was frustrating, a tantalizing curtain drawn shut. Scientists knew the atmosphere was primarily nitrogen, like Earth's, and detected methane and other complex hydrocarbons, but the surface was a complete enigma. Was it a global ocean of ethane, a frozen, cratered wasteland we simply could not see? This blurry orange ball represented the limit of our knowledge for over 2 decades, a persistent question mark hanging in the outer solar system. Then on July 1, 2004, everything changed. The Cassini spacecraft, a marvel of engineering, slipped into orbit around Saturn. Its mission included an intimate study of Titan, equipped with radar and other instruments designed to pierce that opaque haze. The first radar passes were revelatory. Dark, smooth patches contrasted with brighter, rugged terrain. The shapes were unmistakable coastlines, islands, and channels. Titan had lakes, it had rivers, it was a hydrological world, but one built from liquid methane, not water. The abstract chemistry of Voyager had become a tangible, dynamic geography. The crowning achievement came on January 14, 2005. The Huygens probe, named for Titan's discoverer, detached from Cassini and began a 2.5-hour descent through the dense atmosphere. It was a moment of pure exploration. As it fell, it sampled the air and took hundreds of images, revealing an alien sky and a complex landscape below. Then it landed with a soft thud, becoming the first human-made object to touch down in the outer solar system. The images it sent back in its final 90 minutes of life are forever etched in history. They showed a plain of water ice, dark with damp hydrocarbons, strewn with rounded, smooth pebbles. These were not jagged rocks, they were stones worn smooth by flow, lying in what looked for all the world like a dry riverbed. The scene was hauntingly familiar, a snapshot of a rainy day on an alien shore. In a single mission, Titan transformed from a smoggy mystery into a world. Cassini continued its tour for 13 more years, mapping vast seas like Kraken-Mare, watching clouds form and dissipate, and detecting the chemical imbalances that fuel our deepest questions today. From a point of light to a blurry ball to a world with weather, shorelines, and the ingredients for life, our understanding of Titan has evolved at a breathtaking pace, each discovery peeling back a layer to reveal a reality far stranger and more wonderful than we ever imagined. But the journey does not end with Dragonfly's final transmission. The true exploration of Titan's secrets may require us to go deeper, to send machines that do not just land on the shore but dive beneath the waves. Visionary concepts are already on drawing boards at space agencies, blueprints for a future where we become true oceanographers of an alien sea. The most captivating of these is a Titan submarine. Picture a sleek, autonomous vessel designed not for the pressures of Earth's oceans, but for the strange, buoyant, and frigid seas of Kraken-Mare. It would descend through the dark, methane-rich layers, its lights piercing an eternal night. This submarine would carry sensors to map the lake's topography in exquisite detail, revealing underwater canyons, submerged mountains, and the true nature of the lake bed. More importantly, it would have fluid samplers to taste the hydrocarbon soup at different depths, analyzing its chemical gradients. It could land gently on the sediment to drill into the muck, extracting cores that hold a billion-year record of thaw and rain, and just maybe the fossilized or even living remains of methanogens. A submarine is the ultimate tool for testing the methanogen hypothesis at its source, moving beyond atmospheric clues to directly interrogate the environment where life would actually live. It could hunt for those chemical imbalances right in the water column, search for complex polymers with biological patterns, and even look for microscopic structures in the sediments. While technically daunting, requiring new ways to communicate through liquid and manage buoyancy in a fluid less dense than water, it represents the logical, breathtaking next step. To sail an alien sea is the stuff of dreams, yet it is a dream with engineering schematics. Alongside a submarine, other missions target Titan's other great mystery, its interior. Advanced heavy-duty landers equipped with powerful drills could attempt to penetrate the icy crust, not to reach the deep water ocean, which is likely tens of kilometers down, but to search for shallower pockets. Scientists theorize that impacts or geological activity could create localized lenses of liquid water-ammonia mixture trapped within the ice like buried aquifers. A lander could drill several meters down, melting its way through the ice to sample this potentially habitable niche. Finding even simple, water-based life in such a pocket would be a parallel revelation, proving that two separate biospheres could exist on a single world. These concepts, submarines and deep drills, are not scheduled missions. They are visions that depend on what Dragonfly finds, on technological advances, and on sustained political will. But they serve a vital purpose. They remind us that exploration is a continuum. Dragonfly is the pioneering scout sent to survey the territory and send back its report. If that report contains even a whisper of promise, these more ambitious missions will be waiting in the wings, ready to turn our greatest questions into definitive answers. The dark lakes of Titan may hold their secrets close, but humanity is just learning how to listen. From a smoggy dot in a telescope to a world with rivers and lakes, Titan has rewritten our understanding of where life could begin. This journey of discovery has revealed a landscape both hauntingly familiar and profoundly alien, where the very rules of biology may have been written in a different chemical language. The whispers are there in the data, in the strange disappearances of hydrogen and acetylene from the atmosphere, a chemical imbalance that points toward a hidden, breathing world. These are not proof, but they are a compelling invitation, a mystery written in the thin air of a distant moon. And soon we will send an answer. The Dragonfly mission, a nuclear-powered rotorcraft, will become our eyes and hands on that frozen surface, tasting the air and drilling into the organic dunes to read the story written in the isotopes and molecules. It will search for the fingerprints of a metabolism utterly unlike our own. The implications of what it might find are almost beyond comprehension. Confirming life on Titan would not merely be discovering a new species, it would be discovering a second genesis. It would prove that the spark of life is not a singular, miraculous accident on a warm, watery world, but a robust, creative force in the universe, capable of igniting in the deep, cold, and dark, using whatever chemistry is at hand. Our definition of a living world would expand overnight to include hydrocarbon seas under orange skies. We would look up at the night sky and know with certainty that we are not alone in the cosmos, even if our only companions are patient, silent microbes swimming in an alien sea. This knowledge would redefine our place in the universe, transforming it from a cold, empty void into a place brimming with potential, a gallery of experiments in existence. So keep your eyes on Saturn, that golden jewel in the night sky. Remember that circling it is a world of dark lakes and hazy skies, holding a secret that could change everything. Follow the journey of Dragonfly as it builds toward its launch, and stay curious. The greatest discovery in human history may be waiting for us, not in the distant reaches of the galaxy, but right here in our own celestial backyard, a mystery floating in the deep freeze, just waiting to be solved.